Hello, everyone, and welcome. My name is Pratik Bardhan, and today I'll be discussing a recent journal article by Hatzes and his team, where they discovered a new planet and updated some planetary parameters using the radial velocity method. So to start, we're going to talk a little bit about the background of exoplanets. So exoplanets are planets in a different system, a different solar system, orbiting faraway stars. And for the last 20, 25 years or so, finding exoplanets has been a really hot topic. It's one of the biggest fields in astronomy these days. And astronomers want to know a lot of details about these planets. And part of this is motivated by the search for habitable planets. Can these planets be lived on? What are they like? What are their atmospheric characteristics, and what are they made of? And there are several different methods for detecting exoplanets, and they all tell us different things about the exoplanets, different characteristics, but in the end, they all do have the same goal. So the main method that we're going to talk about today is the radial velocity method. To start, all celestial bodies exert a gravitational force on one another. And if you look at the picture here on the left side, you can see a star and a planet and a little X in the middle. And that X represents the center of mass of the system. So while a lot of people might think, oh, all the planets just revolve around their host star, this isn't strictly true. So what actually happens is that while the star exerts a huge gravitational force on the planet does in fact exert a gravitational force back on the star. Most of the time, since the star is so much bigger than the planet, it's hard to detect and it's not really noticeable. But for larger planets, let's take the case of Jupiter, the center of mass of the Jupiter Sun system is actually outside the surface of the sun, although very close, and Jupiter and the sun rotate around this point, or they revolve around that point just outside the surface of the sun, rather than the sun being stationary and Jupiter just revolving around it. And since the star does in fact move, we can actually detect this. So in a faraway system that has a planet that produces a little bit of a wobble, with precise technology, we can capture the movement of this star. And this can kind of clue us in that there might be a planet in that system which is causing the star to have this movement. So how exactly do we do this? Well, we look at the spectra of that star, and if it's moving back and forth with respect to us, the light becomes Doppler shifted. And what this means is that when a star is moving towards us, the light becomes what we call blue shifted, because when the star is coming towards us, the wavelengths get shortened towards the blue end of the spectra. And when the star is moving away from us, the wavelengths get lengthened or redshifted because they move towards the redder end of the spectrum. And when we see a periodic shift in this spectra from the star, we can kind of determine that it's moving back and forth and there's something causing it to move back and forth. And that way we can infer that there is a planet there. Another thing to know about the radial velocity method, because what it does is it helps give us the mass of the planet, which is an important property that we want to learn. But we have to remember that we're only learning the minimum mass. And the reason for this is because we don't know the exact orientation of this planetary system. For example, they could be face on or edge on, like we see in this graphic here. And if the system is face on, we won't see much radial movement relative to us because it all seems to be happening in one plane. So we won't have much of a Doppler signature to go off of. But if the planetary system is edge on, then we can see the maximum Doppler signature because everything will be in the radial direction relative to us. And of course, there's a great number of systems that are in between these two. And that's why we have to use the term minimum mass. So what we do is astronomers use the inclination angle, which is denoted by I. And they say that if the system is face on, the inclination angle is 0. If it is edge on, the inclination angle is 90 degrees. And most planetary systems fall somewhere between these two, and we just have to remember that we're finding the minimum mass of what it is rather than the actual mass if we don't know the inclination angle of the system. So today we're going to be studying the Pi Mensae system. So Pi Mensae is a yellow dwarf star about 60 light years away. It's located in the sky in the Mensa constellation, hence its name. And it's been a source of interest since 2002, when Jones et al. Discovered a planet using the radial velocity method. This planet was on a 5.75-year orbital period. They called this planet Pi Mensa b. And since then, through NASA's tests, they were able to, which searches for exoplanets through a sky survey. They look at the transit method, which is when a planet crosses the face of a star within our line of sight. So sort of, as you can see in the bottom left photo, the planet blocks out some of the light from the star. Of course, they're not always so dramatic as you see in this graphic. Their planets are usually quite a bit smaller than that, but they can still produce a dip in the light that we see from that star. And if you look at the right side, that graphic, it shows how the flux received from the star does dip during a small period of time while the planet crosses the face of the star. And through the transit method, TESS discovered another planet, Pi Mensae c, which is a very small planet orbiting very close to the star. It actually has a period of just 6.27 days. So that's some of the background for the Pi Mensae system. And this is the system that Hatzes and his team were studying. So what they did was they used data from the High Accuracy Radial Velocity Planet Searcher spectrograph, or known as HARPS for short. And this is a spectrograph on the European Southern Observatory's 3.6 meter telescope in Chile. Chile is a good place to observe because they have clear skies, and there's quite a few other telescopes situated there as well. And they use the HARP spectrograph because it can measure really precise changes in a star's radial velocity. And as we talked about for the RV method, that's really important. If we can detect those minute wobbles in the star, we can infer that there's a planet there. So the HARP spectrograph is an important tool in the search for exoplanets. So Hatzes et al. Used archival data as well as some more recent data to find the radial velocity curves, and they wanted to conduct a periodogram analysis. So the first thing they did was they used a best fit program called GaussFit to generate an orbital solution for Pi Mensae b. And you can see in the graphs on the bottom right, the top one is the orbital solution for Pi Mensae b, and it shows the radial velocity over a certain amount of time, and you can see the periodicity there. The bottom graph shows the residuals left over after the contribution from the planet Pi Mensae b was subtracted outwards. And that's important to subtract that out because in the periodogram, which shows the orbital frequencies in inverse days, you can see that the top periodogram on the right has the contribution from Pi Mensae b subtracted out. So there's two peaks there, two large peaks. And the first one is at 0.008 inverse days, which corresponds to 125 days. And this is the orbital period of a new planet that Hatzes and his team called Pi Mensae d. And the second periodogram subtracted out the peak from Pi Mensae d and leaves Pi Mensae c, which is the transiting exoplanet that we talked about earlier, with a frequency of 0.16 inverse days. This corresponds to 6.25 days, which is about what we talked about before, how it orbits very close to the host star. The last periodogram subtracted out all the peaks, and there's no significant peaks left. You can see a couple maybe, but Hatzes et al. Decided that they fell below the false alarm probability limit, which means that any peaks remaining were most likely due to noise or fluctuations in the data and don't actually represent real planets at all. So after doing this, Hatzes et al. Isolated the 125-day signal by getting rid of data from Pi Mensae c and Pi Mensae b. because they just wanted to examine what they hoped was a new planet. And they looked at the power on the periodograms from before and compared it to the number of measurements. They also used a simulation to generate expected data and wanted to compare the two of them. So the real data from Pymense D is shown in blue, and the expected data is shown in red. And as you can see, the real data actually did match the expectations, which would indicate that this is in fact a real planet. So here are some of the findings of Hatzes et al. And you can see in this table, they present their values of the orbital parameters with the uncertainties. So you can see the orbital parameter is approximately 125 days, as we talked about. You can also see the eccentricity of the orbit of 0.22. And at the bottom, you can see the planetary mass, or minimum mass, of 13.38 times the size of the Earth, making this a fairly large planet orbiting fairly close to the star. As we mentioned, it's over 13 times the size of the Earth, and its orbital period is only about a third of the Earth's. So Hatzes et al. Also studied Pymense C in more detail. That was the planet we mentioned earlier that was discovered by the TESS sky survey, the transiting planet. And using some data from previously published papers, as well as their own findings, they calculated its mass to be about 3.63 times that of the Earth. And as from the transit method, they are able to calculate the radius by seeing how much the light was blocked when it crossed a star. And having the mass and the radius you can get the volume, they were able to calculate the density of Pymense C to be 2.03 grams per cubic centimeter. Now, comparing this to other known exoplanets in a similar mass range, this is actually quite a low density. And the large radius of Pymense C and low density indicates that it may have a large gaseous envelope, which would increase the radius. Since the gases aren't very dense, this would cause this would increase the radius by a great deal, while still keeping the density very low. And you can see on the right side here a graph generated by Hatzes et al, but based on data from Zhang et al. And it shows the mass and radius relation for different exoplanets. And it has the curves on there with the compositions of these planets. And you can see in red, near the top left, the point for Pymense C. And it fits the profile closely for a planet with an internal structure composed mostly of pure water. That's the curve it's closest to, although it is a little bit off. So in conclusion, the authors were able to examine Pymense D and find that it is most likely a real planet with an orbital period of around 125 days and a minimum mass of slightly over 13 times that of the Earth. So looking at the data they displayed and seeing how they tested it multiple times, including comparing it against expected results from simulations, this result seems completely plausible, and it's very likely that there is another planet orbiting around Pymense. Hatzes et al. Also updated some planetary parameters for Pymense C, the transiting planet that was discovered by Jones et al. In 2002. And they were able to conjecture that Pymense C has an internal structure of water. This is an exciting find in the search for habitable planets because, as we mentioned earlier, that is one of the motivating factors for attempting to detect exoplanets. Although one thing must be noted is that Pymense C doesn't exactly fit the curve from Zhang et al. So this could indicate that there could be other elements making up a significant portion of the internal structure of Pymense C. However, this is a very recent paper from this month, and other astronomers will be looking to analyze their results, and it'll be really interesting to see if they can prove or disprove them. Of course, that's science. People produce their findings, others can build off them, see if they're right or wrong, always evolving and always changing. But it's a very interesting find from Hatzes and his team, and it'll be super interesting to see where the exoplanet studying field goes next. These are my references, and thank you all for watching.